Hello, hello. Hello. Is the sound on? The sound is on. What's poppin'? Alright. What the fuck? Alright, alright, alright. Uh, we are here to study, and I got to get through. I think this video still. Nope. Is it this one? Yeah, it's this one. So I had my questions answered. And now I know what to do. There's one question on the exam that he said about is it this chapter? I can't remember. The queuing, the priority, round robin, and whatever the other one is. Round. Is it this one? No, it's not this one. This thing. It's first come, first served. Priority, round robin, and weighted fair queuing. So he said there's going to be one question on this. So I think the question might be defining which packet to send next on the link. I'm trying to think, like, what could it... He might be asking which... Not the process of it, but which one it might be. He said it's multiple choice. So... There is that. Alright, weighted fair, generalized. So I understand this. This is literally just round robin with priority. Round robin just goes 1, 2, 3, 1, 2, 3. Priority is based on the priority. And first come, first serve is just packets transmitted in order of arrival. So yeah. I don't even know where I'm at in the slides here, to be honest. I think I'm here. Yeah.
Networks with interfaces terminating the endpoints of the isolated networks, and each isolated network is called as the subnet. So if we have seen over here that there are 6 interfaces over here. Alright, so moving ahead now.
What the hell?
Alright, classful addressing, we already have done that IPv4 address was designed with a fixed length prefix, but to accommodate both small and large networks, and the whole address space was divided into 5 classes: class A, class B, class C, class D, and class E. So this was called as the classful addressing. We have already done this in the lab. So in class A, the class A addresses range from 0 to 127.
I don't need to know this stuff.
class A, the first two bits are 1 and T is not on, and the for the class A. So the and come to it's a
Oh, this I didn't need to.
TIDR notation, although this also we have
Cider.
discussed in our lab class, classless inter-domain routing. It's a internet address, it's a technique to assign the IP address to the devices. So subnet portion of the address can have any length, and the address format is now given as like X, 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 X
Tentacion.
slash Y,
X.
right?
X.
So where X they are the bits in the where sorry Y this Y is the portion in the subnet portion, address of the subnet portion. So if you see over here, this is the subnet part and this is the host part. If I have an address 223.16.0.23, so 32 minus 23, 32 minus
That's
23 is
9.
9. So 9 bits will define the host part, and rest all the bits will define the subnet part. So 23 bits
What's
will
up,
define
Garrett?
the subnet.
I'm just studying. I figured I might as well stream while I study, so. And it's just, I don't know, it kind of forces me to, focus or somewhat, look at it.
part, and the rest 9 bits will define the host part. Now, how to calculate the number of addresses, the first address and the last address in the subnet we have already done in the lab. The number of addresses are calculated as 2 to the power 32 minus n, where n is your slash, whatever is in the slash, bits in the subnet portion of the address. And to find the first address, we keep the left.
That is one of the ones. Uh, is it this one? I don't know if it's this one. One of these we gotta start doing. I think it is this one. Austin teaching me school? Yeah. Uh, it's for my computer networks class.
Most bits set to the right.
Because I've really been studying this exam for this exam for almost nonstop past week. Because if this exam did, hold on, hold on, I gotta check something real quick. Okay, I see what it is. All right. Yeah. So I've been studying this exam for past week because I failed the first one. I got caught cheating, so I got a 0 for it. And this one basically determines if I pass the course or not. And I'm really trying to pass this course because I don't want to tell my mom I got caught cheating on an exam and have to retake a course. So if I get above C on this exam, I should be good. Because then there's the final, and the final I'm gonna do the same thing. Because I just have to get above a 60% to pass the course, and I don't care what my grade is at this point.
Rightmost bits all set to 0, 32 minus n. To find the last address, we set 32 minus n rightmost bits set to all ones, and the address mask is 32-bit number in which the prefix bits are set to 1 and rest.
Yeah, I didn't study for the first one. I wasn't ready for it, so I got caught. Shit sucks, but all they did was give me a 0, so I'm fine with that. But I can't drop the course. So that's another thing is I was gonna try and drop the course depending on what my grade was, but the drop date's this Friday, but I couldn't drop, but because yeah, I had to sign something. But yeah, uh just hoping to pass. This course, because the reason I did it also was because this course is one of the courses that I do not like. I don't care for this course. It's how did I get caught? Because it was like this is Canvas. This is what we call Canvas, and it was like one of these like quizzes things is in here. I opened up like a new tab, but I didn't know they could see my screen. Like the place that I took the test at, they could see my screen. So they knew I opened up a new tab, and that's when they shut it down. Basically, they came in and said, "Nah, get out." Basically, but yeah, it was stupid. I accept it. That's on me. Thing is, I should have just taken the exam normally and taken the F. I mean, it would have been better than a zero, I think, even if I got two questions correct. But I was not prepared for that exam, but this one I'm prepared for. But I'm nervous as hell because I'm afraid he's gonna throw a outlier type question of like, what does this one word mean? And there's two chapters. This one is 94 slides. The second one's 81 slides. Nah, they make sure we don't have our phones. In the testing center that I take it at, they make sure that we don't have our phones. Or like we have to take our phones out of our pockets or whatever. Trust me, I thought of every way, but man, there's no way around that. I didn't know they could see my screen. So, but hey, I live and learn. But I was dumb. That's on me. I accept the L. Like here, let me show my grade. Uh, so yeah, you don't see my name. That's good. Uh, oh, it doesn't matter. My name's already public. Uh, yeah, this is my grade. Oh my god. Thing is, none of these other assignments are like graded yet, so I'm it's kind of annoying because I think this would be like a 58. But hold on, there's one of these. I think this one. He has to make this a 9. Yeah, so that'd be 57. Then all these other ones he has to grade still. So if I assume everything else is 100, big assumption here. Yeah, 57.6, that round up to 58. Yeah, here, first exam, 0. Uh, if I get 50 on this exam, it brings me to a 67. If I get a 75, it gives me 71, which I'll be fine with. If I got a 90, bring me to 75. Now, in the off chance I get 100, I could get a 76, and then there's the final. So, if if all goes perfect, I could get a B in the class, but I'm not expecting to get 100. Because it's half multiple choice and half free response, and the free response ones are kind of iffy. I don't think, if I click on this, I don't think I can see the... No, yeah, he hit it. There was a moment where I could the see the exam, but I don't know. But yeah, so that's why I've been, and then so the scaling, there's two midterms, I guess he would say. Each one is 15%. So that's the only reason why I haven't, well, I couldn't drop the course, but that's why I haven't really been too stressed about it, because this is the inclusion of, where is it? Here. So because he didn't separate them, because he should have separated these two exams into 15%. But right now my grade should actually be like a 65 or something. So there's that. Because technically it's only 15% from the first one. The other 15% isn't even here yet. but and then the final's 20. So he has to fix the quiz grade, and then everything else has to be, I don't know. Like, I just have to make sure I pass this exam. At least over a 50%. But, yeah.
So here we have,
What the hell is this?
so we have the first address. We will set 0 to
I think
minus
this is
0,
the
that means
subnetting.
address and alright, in the way of identifying it.
One thing I am glad about is the final's not cumulative. None of the professors now do cumulative finals. I don't know if that's like most colleges or if that's just mine, but they aren't doing cumulative finals because there's not enough time. I never understood that in high school or even in my community college. Everything was cumulative, and that shit was so stressful and annoying.
Dot 12 subnet mask out the example 000
Alright, I don't need to know all this.
using within the organization or service
I already know.
gets the IP addresses from licensed content. So ISP among this one, these are the host bits. Host bits are 32 minus 20, which should be 12. Now this large block is distributed to 3. I just
Alright, hold on.
mentioned Internet Corporation for Assigned Names and Number. It's an organization which is
I
responsible.
thought... Where was this? Oh, so she did. This is over. But I understand. I understand this.
For distributing the IP addresses to the different internet service providers. It's a non-profit organization in California, and its role is to allocate the IP addresses. It manages the domain name root servers, and it assigns the domain names, and it resolves the domain name dispute. So these are the functions or the responsibilities of the ICANN. How does host get the IP address? Once organization has obtained a block of addresses, it can assign individual IP addresses to the host and the router interfaces in its organization. So once a basic organization has got a block of addresses, it can then distribute or assign those individual IP addresses to the various devices and the router interfaces in the organization. Okay, now system administrator will configure the IP addresses into the host, and most of the time this task is now done by the DHCP protocol, dynamic host configuration protocol. We discussed this time in the lab also, and the purpose also. DHCP, the purpose of DHCP is to automatically get the IP address from the DHCP server. So when you first switch on your system, or when you first switch on your system, the first thing that your system does after, of course, after booting and after loading the operating system, what it does is it first of all contacts the DHCP server of the organization. Now, after contacting the DHCP server, it gets its IP address from the pool of the IP addresses stored in the DHCP server. So, DHCP server allows a host or a device to obtain an IP address automatically. Now, who configures this DHCP server? This DHCP server is configured by the network administrator of the organization. A network administrator can configure the DHCP so that any host receives the same IP address each time it connects to the network. Or host may be assigned a temporary IP address also. If it is assigned a temporary IP address, then every time when the host connects to the network, its IP address will be different. Okay, now let's talk about more about DHCP server. So the goal of the DHCP server is to allow the host to obtain its IP address from the DHCP network server when it joins the network. DHCP, because it uh, automates the network related aspects of connecting a host to the network, DHCP is also called as plug and play protocol. So this capability actually makes DHCP very attractive to the network administrator. Otherwise, the network administrator will have to do this task manually. Let's understand this DHCP in very simple language. Consider yourself. You are a student and you normally use laptop. So, for example, you are moving from building A to building C, or from classroom to the lab, or uh, from building B to building C. Now, it is more likely that in each location, your laptop will be connected to a new subnet, and when you move from building A to building B, we have router for building B separate, and we have separate router for building A. So when you move from building A to building B, your system will need a new IP address at each location. So in this case, DHCP is ideally suited for this situations because many users will be coming and going, and addresses are needed only for a limited
Alright,
amount.
to be honest, I was not paying attention
And
to what she
when you
just
move,
said.
it is more likely that in each location, your laptop will be connected to a new subnet, and when you move from building A to building B, we have router for building B separate, and we have separate router for building A. So when you move from building A to building B, your system will need a new IP address at each location. So in this case, DHCP is ideally suited for these situations because many users will be coming and going, and addresses are needed only for a limited amount of time. I can give you another example. Consider a large residential society, which a large residential internet service provider. It has 2,000 customers, but at a particular time, not more than 100 or 400 customers are online at the same time. So in this case, if we permanently assign IP address to all the 2000 customers, it will be a wastage. So a block of just 2048 addresses for a DHCP server that it assigns addresses dynamically, it will need only a block of 512 addresses. So when the host joins and leave, DHCP server needs to update the list of available IP addresses, and each time host joins, DHCP server will allocate any arbitrary IP address from the current pool of available addresses to the newly joined host. So this is how the DHCP makes the life of the network administrators easier. Also, host in addition to the host IP address assignment, DHCP also allows hosts to learn the additional information such as subnet mask, address of the first hop router, which is called as the default gateway. We learned what is default gateway in the class, and address of the local DNS server. So DHCP server makes the host to learn all these things also in addition to the IP address assignment. Now, how this process is uh, initialized, or how this process is carried on, the assignment of the IP address to the host by the DHCP server. So to indicate the
Yeah, I just had to remember Dora. Discover, offer, request, act, host, DHCP. DHCP, dynamic host configuration. Host dynamically obtains IP address from network server. Isn't this basically all of like what? I'm trying to think. Isn't this basically just a subnetwork? No, subnetworks. You can communicate with another device without going through the router. So CIDR, but then again, why IP wait, IP host? How does host get IP address? Dynamic.
Address being allocated to the newly arriving client. So there are 4-step procedures. First step is host will broadcast that I am on the network, I have come on the network. So host will send the DHCP discover message because it wants to discover the DHCP server. So to all the servers, to all the nearby computers, this discover message will be sent. Broadcast means sending it to everyone. Now, who will respond to this DHCP discover? Only the DHCP server. So DHCP server will respond to the host and that message is called as the DHCP offer message. Now host will send another. Now when DHCP server has responded to the host, now host knows the IP address of the DHCP server. So the third message that host will send, it will not be broadcasted. Only the first message is broadcasted. Now host will send the message to the DHCP server and it will request for the IP address, and that message is called as the DHCP request message. Now DHCP server will send the address and that message is called as the DHCP acknowledge message. So these are the 4 steps. Only the first message or the first communication is broadcasted. The third communication is not broadcasted. So if you see over here how it does, let's understand the complete scenario of this one. Okay, so here is the DHCP server. All these systems are already having the IP addresses. Now arriving DHCP client, we have some just I told you that you are a student, you may be going to another building from building B to building A. So your system will connect the DHCP server. So arriving DHCP client needs address in this network. So how it will be done? So this is an arriving client.
Hey, we're almost done this video. 28 minutes
left. Does not have the, when the client arrives, it does not have the IP address. So what it will put, it will send the discover message. When it is sending the discover message, what it will do in the source address, it will just put 0000 and this is the port number 68, because we understood in the Wireshark class that the DHCP messages are sent on the port number 67 and 68. 68 port number we just now 125 and it uses port number 67.
He took out all that, so the extra notes here, I guess I don't need to know that.
So remember, so this
lifetime
client 60 CP access for address of the gateway, address of the gateway, name and IP address of the DNS local server and the subnet mask. So these are the 4 things that the DHCP server returns to the client. Alright, so we have finished with the first part of our today's lecture. So first of all, we are going to talk about network address translation.
This is the part that I don't have much knowledge about.
NAT router.
Or like I understand it, but I don't have much studying with this section.
Okay, before going to the NAT, I will like to mention a point about the DHCP server. DHCP discover message and DHCP offer message, both the messages are broadcasted. DHCP server discover message is broadcasted because the client doesn't know what is the IP address of the DHCP server. DHCP offer message is broadcasted because there can be many other DHCP servers. It's not only one DHCP server. So it is broadcasted to let others DHCP server also be aware about that I have sent it the IP address or I have contacted the client. So basically several DHCP servers can be present, so client may find itself in the enviable position if to choose from the several offers. So that's why it is broadcasted. Now let's come to the network address translation, NAT router. What is a NAT router? Let's first of all have a small discussion on it. We know that every device needs an IP address. So changing technologies and changing scenarios, we have a small office, home office, subnets, and also it will imply that if we have a small office or home office, we want to install a LAN to connect multiple machines, a range of addresses will need to be allocated by the ISP. So if our subnet grows bigger, for example, we have kids at home, they do not have only their computers, but they have like iPads, or they have smartphones, iPhones, and even the network enabled game devices, we need a large block of addresses. So what will happen if internet service provider has already allocated contiguous portions to your network's current range, and what if a typical homeowner wants to know how to manage the IP addresses? So there is a simpler approach of address allocation, and which has found a widespread use, which is called as the network address translation. So if you see over here, this diagram actually shows the operation of the network NAT router, network address translation router. So for example, if you see over here, let's assume that this is our home, and we have this is the IP address, block of IP address given to us, 10.0.0.4 24/24, and these are all the addresses, address of the devices in our home: 10.0.0.1, 0.0.2, 0.0.3, and 4, 5, 6, and so on. And this is the address of the NAT router. So datagrams, whatever the messages or the datagrams with the source or destination address in this network have 10.0.0.24 address for source and destination as the usual. Now all the datagrams leaving this router will have the same single source network IP address. So for example, this system sends some message. So when it comes over here, the message will have the IP address 10.0002. But when it comes to the NAT router or the NAT router, because all these systems, they are connected to the same router. So when it leaves this router, it comes to this router, this NAT router will assign the IP address 138.76.29.7 to this system. So all the datagrams that leave this local network have same single source net IP address, which is 138.76.29.7, different source and port numbers. So I can say that this is the IP address which is visible to the rest of the network, or which is my public IP address, and this is my private IP address, a sort of private IP address. So the motivation behind.
Hold on, I gotta open something else up.
I told you local network users just one IP address as far as outside world is concerned. So it doesn't matter how many devices are you using at your home. So whatever the message you send from different kinds of devices, it will always have one IP address to the rest of the world. So range of addresses need not to be needed from ISP, just one IP address for all the devices. It can change the addresses of the devices in the local network without notifying the outside world. It can change the internet service provider without changing the address of the, you can change the ISP without changing the IP address, and devices inside the local network need not to be explicitly addressable or seen by the outside user. So this is my sort of public IP address and a private IP.
I guess motivation is. What the hell is motivation? Hold on.
And 4, 5, 6, and so on. And this is the address of the net router. So datagrams, whatever the messages or the datagrams with the source or destination address uh, in this network have 10.00.24 address for source and destination as the usual. Now all the datagrams leaving this router will have the same single source network IP address. So for example, this system sends some message. So when it comes over here, the message will have the IP address 10.0002. But when it comes to the NAT router or the NAT router, because all these systems, they are connected to the same router. So when it comes, leaves this router, it comes to this router, this NAT router will assign the IP address 138.76.29.7 to this system. So all the datagrams that leave this local network have same single source net IP address, which is 138.76.29.7, different source and port numbers. So I can say that this is the IP address which is visible to the rest of the network, or which is my public IP address, and this is my private IP address, a sort of private IP address. So the motivation behind, I told you.
Alright, I feel like. Hold on, let me check something real quick. Thought there was a quiz question. Something like this. Let me see. Let me see. Let me see. No, yeah, receive datagram from the router will change the router's. Wait, change the datagram's source IP and source port number. Let me just make sure the source IP and source port number. Alright, I think she'll go more over about it, but yeah, that's correct. Yeah, this was stupid of me. I should have figured. If I had studied this further, I would have known. Yeah, let's continue watching.
Local network users just one IP address as far as outside world is concerned. So
Oh wait, so let me think. The congestion control. I think it's is it congestion control. It's end to end. It doesn't give direct feedback, and it infers on the packet loss, I think. Something about inferring on the packet loss, or the lost packets. Um, the other one is network assisted control. It gives feedback to the host, I believe, and what else does it do? It can, I believe it can set a limit or something. Let's see. It's at the end of this chapter. Is it in flow control? No, it's inferred from congestion inferred from congestion and then may indicate congestion level or exclusively set sending rate. So set wait, feedback, so provide feedback to the host. Okay. So I got that part right. May indicate congestion levels. Yeah. Alright.
Doesn't matter how many devices are you using at your home. So whatever the message you send from different kinds of devices, it will always have one IP address to the rest of the world. So range of addresses need not to be needed from ISP, just one IP address for all the devices. It can change the addresses of the devices in the local network without notifying the outside world. It can change the internet service provider without changing the address of the, you can change the ISP without changing the IP address, and devices inside the local network need not to be explicitly addressable or seen by the outside user. So this is my sort of public IP address and a private IP address, I can just say like that. Now what NAT routers must have? NAT router should have outgoing datagrams should replace the
Here
source
it is.
IP address and the port number of every outgoing datagram should be replaced with IP address of.
Yeah, so source outgoing is replaced with this incoming. This is incoming, right? The NAT replace. It's flipped. Like I feel like if I get a question, I will understand it, but I just need to remember one of them, I believe, because I'll understand the other one's flipped.
The NAT router and the new port number. Remote clients and server will respond to the, when remote client and server they will respond with the NAT IP address and the new port number. So when that message arrives, now this NAT router will be responsible for changing to the original source IP address and the port number of the machine. So in NAT has a NAT translation table. So every source IP address port number to NAT IP address new port number translation pair it saves. Incoming datagrams replace NAT IP address and the new port number in the destination fields of every incoming datagram with the corresponding source IP and port number stored in the NAT table. Now what does this mean? Let's understand. For example, now this let's assume that this system 10003 has sent a message. So what IP address it will use? 10003, and let's say port number the port number.
Hold on, let me check something real quick.
$520. When it comes to this NAT router, now this NAT router will replace this IP address with its own with this address. Let's assume 138.76.29.7 and some port number, let's say 1020. So when the message reaches to the destination, that person or that device will see this IP address and not our real IP address. Now when that device responds to us, it will use this NAT router's IP address and the port number. So when the message arrives at the NAT router, now NAT router, what it will do, it will have a NAT table, translation table. It will look into this translation table where it has the NAT IP address and the original IP address pair. So it will replace this IP address with this system's IP address and the port number, and then send it to this system 10003. So this is a sort of private IP address and a public IP address. So NAT router, it should do three things. Outgoing datagrams should be, it should replace the source IP address and the port number of the outgoing datagrams to the NAT IP address and the new port number as the destination address, so that client servers will respond using the NAT IP address and the new port number address as the destination address. In a NAT router must update or maintain a NAT translation table, which should have source IP address, port number, and NAT IP address, new port number. Now all the incoming datagrams, when incoming datagrams arrive at the NAT router, it must replace the NAT IP address and the new port number in the destination field with the corresponding source IP address and the port number stored in the NAT table. So this is all the things that NAT router should do. So this is what I just explained you. For example, same thing I just explained you. For example, this is the NAT table, NAT translation table. So for example, it sends the message using the port number 3345, and this is the destination address, and this is the destination port number. So when this arrives, when the message arrives at the NAT router, so what NAT router will do, it will look into the translation table. Instead of source IP address, it will put this IP address 138.76.29 and 7, and the port number is 5001. Destination address will be the same. Now the machine, the destination machine, will see this IP address and not our device IP address. This is our public IP address. Alright, now when the machine sends some message to us, it will use this IP address 138.76.29.7 and the same port number as the destination address. So when this arrives at the NAT router,
Alright, NAT router, I feel like network address translation. Basically, it's like masking our IP address. Yeah, hold on. Alright, okay. Hold on. I was just responding to a message.
Router changes the destination IP address from 138.76.29.7 to 10.0.0.1.3.3.4.5 and delivers it to the same.
Alright, so look at this. So, this is in our table. This is, it translates to source IP NAT. So this is the NAT, I guess. This is the NAT IP address. What is this? This is our NAT, and then this comes back and translates back to this. Which, wait, our source stays the same, but then our destination, it translates back.
System. So this is how the NAT router works. Alright, next we talk about ICMP very quickly. Although we have done the ICMP protocol in the Wireshark lab.
Yeah, ICMP's like, I have no idea where these notes are, cause it's what? Oh my god. Was it in here? Oh wait, no. What does ICMP stand for? Internet Control. Right, I could have sworn ICMP was in here. What? Let me see. Yeah, I have a feeling this last stuff here I'm not gonna know about.
It is used by the host and routers to communicate network level information. It is used to for error reporting. ICMP is
Might
basically
be why we don't
and
go
reply.
over it.
Its structure
Oh, it's DCHP or whatever. That's what I'm getting it confused with.
are other IPv6. So 32-bit IPv4 address will soon be replaced completely
Soon.
by IPv6. So 32-bit IPv4 address space soon to be completely allocated. It will be completely exhausted. So we need some other thing, and now the solution is IP version 6. So what is IP version 6, and let's understand about it. IPv6 increases the size of IP address from 32 to 128 bits. So in IPv4, the size of the IP address was 32 bits, or we say that 4 bytes. And it becomes now in IPv6, the size of the IP address is 128 bits. 128 bits means 16 bytes. So if you see, there is a 4-time increase in the size of the IPv6. It has a fixed length 40 byte header, whereas in the IP we have 20 byte header, right? We have seen in the Wireshark lab. So it has a fixed length 40 byte header. There is no fragmentation or reassembling allowed, but this is allowed in the IPv4. These are the differences. No fragmentation or reassembling allowed. It is allowed in IPv4. And no checksum value. There is checksum value in IPv4. So these are the few differences between the IPv4 and the IPv6 datagram format. Alright, so this is the datagram
Hold on.
format. If you see,
That's definitely going to be a question. Is what's the difference between IPv4 and IPv6? That's definitely a question, no doubt about it. Alright, hold on. IPv4 has checksum. So basically, I'm gonna just say IPv4 is is it 32 bits, whereas IPv6 is 128, and then no fragmentation, no checksum, and it should be good. So I need to remember that.
It's simpler as compared to the IPv4, quite simpler. So it has version, traffic class, flow label, these are 32 bits, then payload length, next header, hop limit, source address is 128 bits, destination address is 128 bits, and data is variable length. Alright, so what are these sizes? Version is 4 bits, it identifies the IP version. Traffic class, it's an 8-bit field, similar to the type of service field. We have IPv4 type of service, normally may be used for upper level protocol, for example UDP or TCP. Flow label is a 20-bit field. Flow label is a 20-bit field used to identify flow of datagram. So 20 plus 828 plus 432. So if you see, all these three takes 32 bits. Payload length, it's a 16-bit value, and it is an unassigned integer giving the number of bytes in the IPv6, followed by the fixed length 40-bit datagram header. So payload length, what is the, just like in IPv4 we have the total length, so this is the payload length. So how much length of the total length of the IPv6 datagram. Next header, if you see, we have the next header and the hop limit. Next header identifies the protocol to which the contents of this, okay, so this specifies TCP or UDP. This specifies the type of service that we are using. So the field uses the same value as the protocol field. So the next header field is similar to the protocol field in the IPv4, which specifies the protocol used by the next higher layer, which is TCP or UDP. Okay. Hop limit. Hop limit, the contents of this field are decremented by 1 each router that forwards the diagram. So if the hop count limit reaches 0, datagram is discarded. So hop limit actually tells how many hops some field is put. For example, 12. Let's put 12 in the hop count field. So when it crosses first router, it is decremented to 11, then 10. So when hop limit reaches 0 and still the datagram has not yet reached the destination, it will be discarded and the sender will have to send the datagram again. Source and destination, so this is the IP address of the source and the destination. Data is the payload portion, which is the user data of the IPv6 datagram. Alright, other changes from IPv4, checksum has been completely removed to reduce processing time at each hop. Options allowed but outside the header, which is indicated by the next header field. ICMP version, it's a new version of ICMP, and additional message types are also there. For example, packet too big, multi-classed group management functions are also included. If I go back, routers structure, and not all message type like the packet size is too big. Fragmentation and reassembling is done in the host only, and it is not in the routers anymore. Transition from IPv4 to IPv6, because we already have the infrastructure and not all the routers can be updated or upgraded at the same time. So how the networks will operate with mixed IPv4 and IPv6 routers? Because if you see, some of the routers, they use IPv4 addresses, and some systems they use IPv6 addresses. So for example, if a host sends message, the source or the destination address is belongs to the IPv6, but the network router it is configured to have IPv4. So how it will operate with the mixed version of these addresses? These We have a process or a technique
Oh,
called
mouse head.
tunneling.
Hold on. Oh wait, that's his composed tweet. No. They said, someone, hold on. Hold on. Apparently they hacked, Gilbert Gottfried's Twitter. Bro, what the fuck? So I guess, I mean, he has no profile picture. Uh, Yeet archive. What the hell?
So in tunneling, IPv6 datagram is carried as a payload in IPv4 datagram among IPv4 routers. So how this all happens? Let's understand this tunneling scenario. For example, let's assume I have over here 1, 2, 3, 4, 5, 6. I call it as, these are all routers A, B, C, D, E and F. Let's assume that these work on IPv6 version, these work on IPv6 version. These are the sender side routers and these are the receiver side routers. They also are configured for with IPv6. But intermediate routers in the network, they are configured with IPv4. So how does, when this IPv6 arrives at this IPv4 router, how it will forward or how it will do send the how it will recognize the datagram. So this process is called as tunneling. Tunneling solves the problem. Yeah, the basic idea behind this is that now we have assumed that the two IPv6 nodes, for example B and E, over here, they want to interoperate using IPv6 datagrams, but they are connected to each other with the intermediate C and D routers, which are IPv4 routers. So intervening set of IPv4 routers, they are referred to as the tunnel. So now with tunneling, IPv6 node, for example, this is on the sender side B, on the sender side, it will take the IPv6 datagram and it will put into the data or the payload field of the IPv4. So what happens when it arrives over here? It recognizes it as it puts it into the it puts it it what it puts
Spit
because
it
the next
out.
datagram is the IPv4, next router is the IPv4 router. So what it takes, the B takes the entire IPv6 datagram. So it takes the entire IPv6 datagram it can take because it is configured like this. So what it will do, it will make IPv4 field and puts the IPv6 datagram in the payload field of the IPv4. So now IPv4 datagram is addressed to the IPv6 node on the receiving side. This now here when this IPv4 datagram is received, here it forms a tunnel over here. Tunnel is formed over here. So the IPv4 datagram, when it reaches to the receiver side, for example E router, and sent to the first node in the tunnel, the intermediate IPv4 routers in the tunnel route this IPv4 datagram among themselves as if it is any other datagram. So The IPv6 node, this E node on the receiving side of the tunnel, receives the IPv4 datagram. It determines that IPv4 datagram contains an IPv6 datagram. It will extract that IPv6 datagram and then route that IPv6 datagram to the receiver exactly if it had received the IPv6 datagram. So this is how basically the idea is forming a tunnel is IPv6 datagram is put into the payload section of the IPv4 datagram. So this is how a tunnel is formed. So IPv4 header fields, source destination fields. This is IPv6 datagram and this is IPv4 datagram. So IPv6 datagram is put into the payload field of the IPv4 datagram. From IPv6 we make the IPv4 datagram. This is the idea behind the tunneling. So that's all about this lecture for this week. We will
Alright, tunneling and encapsulation. Logical few. I know there's interactive problems on this, so. And then there's generalized forward, open flow, which, as far as I'm aware, look at this. So 953, 365, 379, 182. Let me refresh. Nine, 983, 384, 390. Yeah, people definitely in my class been watching this. That's for sure. Uh, but no, she doesn't have any about the flow table. Flow defined by header values, generalized, forwarding, match, patterns. If I remember, map C, match actions, priority counters. Flow table. Wait, is the flow table the? Is that the? Oh, that's the not translation table. Thought it was the same thing. Hold on. Wait. Each router contains a forwarding table, aka flow. So a flow table is just a forwarding table. Let me get this right. Match plus action, abstraction, match bits, take action. Wasn't this like mentioned in the beginning? Hold on. Hold on. I know it is mentioned here. Ah, wrist. Thought there was something else that it was mentioned. Here, generalized forwarding. Alright, hold on. Simple packet handling. Wait, there's a... Guess I could do this. I didn't even learn how to do this yet. Hold on. This, for... What? Packets coming from the source network S1 destined... Des, des, destined? Is that destined? I can't remember. To the network attached to S3 should be forwarded to the paths S1 to S4 to S3. Okay. For routers, what should the value of the IP source be? I don't fucking know, bro. Where the packet originated from. What? Oh, wait. Oh. For router S1, what should the value of the IP destination be? Pick either specific. Wouldn't it be based on what was said this? S1 to S4. That's the oh, wait. Okay. The source port? Wouldn't it just be... Oh wait, would it be this? Because it's... No? For router, what should the source port be? I don't fucking know. Bro, what? Unless the router needs to block packets. Oh. What is the destination value? Didn't we just do this? Think it'd be any, right? Yeah. IP proto? The hell is proto? What is proto network layer? Uh, this looks like it's gonna be TCP. Nope. Nope. What, for S1, what should it be? I think it should be forward, right? What interface? Bro, I don't know. Be the ones attached to the, what's that mean? S4? The interface will be the one attached to the next router in the packet's path. I'm going to say safely and assume this will not be on the exam. Unless... So... Because I'll email him, my professor, and try and find out, but... Hold on a second. Oh, my Facebook page isn't loading. That's funny. Alright, I'm going to assume that that's not on there. This, how do you know if it's public or private? Like, Like, are these, will these always be private? Do 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 do. Bro, what? Bro, what is going on? Alright, what am I doing? Uh, uh, some reason I decided to go on YouTube and check my YouTube channel real quick. It doesn't matter, I'm gonna be live for like the next 4 hours anyways. Alright, how many hosts can be in here? Well, 24 plus 45, that's 69. And I believe 2 to the 7 is 96. Let me get my calculator out. 2 to the 7, 128. 2 to the 6. Wait, what? So we need 2 to the 7, so it'd be 126. What? Hmm. Or wait, no. It'd be 32 minus 7, and then... Bro, what the hell? Oh wait, we already had 32 minus 24. 2 to the 8 minus 2, which is 254. What is the subnet? Do 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 do. The subnet address, bro. This always gets me fucked up here. Subnet, I believe, is the first one. The CIDR notation. So if it's 24, that means 24. 2 to the 4, 2 to the 5. 32 minus 5, 127. 'Wait, think it'd be that, right? No, this. 2 to the 7, 2 to the 5, 32. 32 minus 5 is 27. Bro, what the fuck? Oh, wait a second. The next subnet address will always be bigger than the previous one. It will always be one bigger than the broadcast address. I give up. 64? Why is it 64? What? 2 to the 5, 32. I'm gonna restart this. Hold on. Alright, I'm gonna guess private. Public. Hold on. Let me refresh this. How do you know? Public. 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 How? '70? Or hold on. How to know if subnet is public or private? Do, 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 do. What the fuck? That probably lagged my stream. Hold on. How do you know if it's routed to an internet gateway though? Huh. Wait, where's Do 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 do. Nope, it's not in our notes, so I'm assuming I don't need to know. But what I do need to know is the first part. How many hosts can be in here? Well, that's simple. It's 32 minus 23, 2 to the 9 minus 2, which is 510. What is the subnet address of A? This is what I did last time and it said it was wrong. So let's try that again. That's literally what I did. So 2 to the 5, 2 to the 6, wait, 2 to the 6, 32 minus 6. So it would be 70.17.190.0/26. How, what? Cider notation, it's this. 70.117.190.0/26. Why is it saying otherwise? What the fuck? What is the subnet address of... It's literally 39. So I do 2 to the... It has to be 2 to the 6. 32 minus 6, 26. I don't think this thing understands what the hell I'm doing here. $191? Why is it 191? What? Huh. What is this? Two, it's gonna be like 2 to the 5, right? What? I don't get this. I don't get it. Doesn't make sense to me. I give up. I give up on it. Because he only gave us one example of subnetting, but it doesn't make sense because I don't get it. What is this? Point 32? How? think this is gonna be 510 again. Nope. Subnet address. It'll be 211.128.0 slash, I think it's gonna be 28, right? 22 to 4. No, it's gonna be 27. Bro, I have no idea why this is so difficult. What is the subnet of A? So this should be right. 64. Bro, 2 to 5 is 32. These are wrong. Pretty sure. How many hosts? It's 23, so that's 9. It would be 510. It's 27, so that's gonna be 27 right here. No. 2 to 5 is 32. I'm gonna just put 64. I don't get it. I don't get it. Why is it 64? Hmm. Alright. So let's get back to this. Uh-huh. Open flow table. Let's go back to chapter 3. Is this the first video?
Hello everyone. So this is week 4.
Week 4. I'm gonna let this load. While that loads, let me see this. Uh, so, longest prefix matching, packet scheduling, subnet addressing, network address translation. Did I do this? What is the source IP for this address? Uh, suppose the host IP address of destined to the host The source port is 3499 destination. So what is the source IP? I believe this would be that. What is, at step 1, what is the destination address? Or the destination IP? Destination IP is this. No. Oh wait, is it this? Hmm. Oh, wait. Okay, that confused me there. Step 2. What is the source IP now? What is the destination IP? Uh, wait, no, it would be this. No. Would it then be this? Will the source port have changed? Yes. What is the source IP of step 3? It's gonna be this. Hmm. Bro, I just literally tried. What? What is the source IP? I've tried all the IPs that's been listed. I thought I must have mistyped it. What is the destination IP address for this datagram? Step 4. It's gonna be 80. No. 3499. What? Then why is the port numbers there? What is the source IP address? At step 4, it's gonna be this. Hmm. Bro, what? Alright, let's try again. At step 1, what is the source IP? Bro, what is the destination IP at step 1? I would say it's this. Nope. At step 2, what is the source IP now? It's the new one. What is the destination? Bro. I've tried them all. Step 3, what is the source IP now? And the source IP is the same thing. What's the destination IP? It's gonna be this. What is the destination IP? Let's try again. We're doing it, we're doing it, we're doing it live. What? Oh. What is the destination? What is the source? What is the destination? It's gonna be... Oh, the ports have changed. Yes. Just before it is received, what is the source IP? Destination IP. What is the source IP after? Source IP after is gonna be this. What is the destination IP? Doo -doo -doo. What is the destination? Doo -doo 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 -doo. The source. What? Did I misspell it? Oh, it's 185. It's the destination. I think the last one will always be no. Alright, where's the...
we are going to start with another new chapter, which is chapter 3, and we are going to start with the another layer of the TCP IP model, which is the transport layer. As I discussed in my previous lecture, that we are going to follow the top-down approach, discussing each and every layer in detail. In my previous lecture last week, we discussed about the application layer in detail. What are the applications and what are the protocols related to that layer? So this week we are going to start with the transport layer. In this chapter, we are going to understand the principles behind the transport layer services. We have already learned that the two important protocols of the transport layer are UDP and TCP. So we are going to learn more about these protocols. So these are the topics that we are going to cover in this chapter: transport layer services, multiplexing, demultiplexing, UDP, principles of reliable data transfer. I have divided my lecture into two parts. So in the first part, I'm going to cover until principles of reliable data transfer, and in the second part, I will cover the rest of the chapter. So start start with this chapter. Let's first of all just talk about transport layer services and the protocols. So transport layer actually provides the logical communication between the application processes which are running on different hosts. What do we mean by logical communication? We mean the meaning of logical communication is that from an application's point of view, it looks like if the hosts running the processes were directly connected. That means the machines which are running the processes, they are directly connected. It looks like from the application's point of view, just like for example when you are using any application layer protocol, for example HTTP or even messengers, it seems like to you that you are directly connected to the receiver or to your friend. So this is what we mean by the logical communication. But in reality, the host may be on the opposite side of the planet. Of course, it's true, it's a reality. For example, you are trying to browse Berkeley University page. It's not here, the Berkeley University server, it's not in the Saudi Arabia, it will be somewhere in USA. So when you try to browse that page, to you it looks like that the host, the machine to which you are connected, or to the application which you are connected, it's quite near to you, but actually it can be on the other side of the planet, and it is connected through many routers and many types of link. Application processes use the logical communication provided by the transport layer to send the messages to each other, and they are free from the worry of the underlying architecture or the physical infrastructure. Now, if you see in this figure, here in this figure, we have the devices connected to the routers. Transport layer protocols are implemented in the end system. So transport layer protocols, they are implemented in the hosts. They are not implemented in the network core or the intermediate devices. Transport layer protocols are not implemented in these routers. On the sending side, the transport layer, so on the sender, at the sender side, the transport layer converts the messages it receives from the application into the transport layer packets, which are called as segments. We learned about it in the chapter 1. And in the receiver side, it reassembles the segments into the messages and then passes it to the application layer. So more than one protocol, more than one transport protocol is available to the applications, and we have two protocols which are TCP and UDP. Alright, so moving ahead, so this is logical end-to-end transportation. Okay, let's understand the relationship between transport layer and the network layer. We know that the network layer is below the transport layer. Transport layer lies above the network layer in the protocol stack, and the transport layer provides logical communication between the processes running on different hosts. Now, a network layer protocol, it provides logical communication between the hosts. So it provides logical communication between the hosts, whereas transport layer provides logical communication between the processes. Processes are nothing but your application. So transport layer relies on reliable and enhanced network layer services. So it relies on the network layer services. Let's consider an example over here, which is given in your book. Let's assume that there are two houses. There are two houses. One is on the other side of the globe, and another one is on the another side of the globe. In your book, it's mentioned East Coast and West Coast. Now, each house uh, in a home has being home to a dozen kids. So each house has 12 kids. There are 12 kids here and there are 12 kids here. So let's assume this is East Coast and this is
Alright.
so one, and the mail and distribute the letters to the mail. Quite good example in understanding how the transport layer is related to the application messages that you send by using any of the services. They are letters in envelope. Hosts are houses. Transport layer are an and bill, and network layer protocol is the postal service, which includes the mail carrier also. So it's a quite good example in understanding the relationship between the transport layer and the network layer. All right. So continuing with this, uh, we talk about internet transport layer protocol. So in the last week, we learned about that the two important transport layer protocols are TCP and UDP. TCP is a connection oriented reliable protocol, whereas UDP is a connectionless unreliable protocol. So TCP is reliable in order delivery. It has congestion control, flow control, connection setup. So connection setup is required. Whereas UDP is unreliable. It's a connectionless. It's unordered. Services not available with these are delay guarantees and the bandwidth guarantee. These are uh, these are not available. Uh,
I need to remember that. Delay guarantees, bandwidth guarantees. Not available. Delay guarantees, bandwidth guarantees. Delay guarantees, bandwidth.
with these protocols. Now let's talk about important concept of multiplexing and demultiplexing at the transport layer. So as we know, multiplexing, you might have learned the term multiplexing in your digital logic also, many to one, and demultiplexing is one to many. Alright, so what is multiplexing and what is demultiplexing in terms of transport layer and how it is done? First of all, let's understand what is multiplexing. Multiplexing means gathering data from multiple sockets, from multiple applications, enveloping data with header, and which can be later used for the demultiplexing. Let's understand more about this multiplexing and demultiplexing. Alright, now we have some diagram over here. The yellow part represents the socket and the blue circle represents the process. So multiplexing means gathering data from multiple sockets or from multiple applications, enveloping data with the header, which can be later used with the demultiplexing. So let's understand how it happens. How now multiplexing occurs at the source host. and demultiplexing always occurs at the receiving host. So always keep in mind, transport layer has the responsibility of uh, delivering the data in the form of segments to the appropriate application process running on the host. So let's take an example. You are using a computer and you are using downloading some web pages
What?
while you
Alright, hold on. I kind of
occurs
blanked
at the
out.
source host, and demultiplexing always occurs at the receiving host. So always keep in mind, transport layer has the responsibility of uh, delivering the data in the form of segments to the appropriate application process running on the host. So let's take an example. You are using a computer and you are using downloading some web pages while you are running a FTP session also and two telnet session also. So when you are downloading a web page, that means you are using HTTP, right? Apart from HTTP, at the same time you are running FTP session also, and you are using two telnet sessions also. So you have now four application processes which are running, two telnet processes, one FTP and one HTTP process. So now when the transport layer of your computer receives data from the network layer, so when the transport layer receives the data from the network layer, it needs to direct the received data to one of these four processes, right? So how it is done? Because the data which is received from the network layer by the transport layer, it should be directed to the correct application for the application for which the data is meant. So let's see how it is done. Now a process can have one or more sockets. We understood the sockets in the previous lecture also. Sockets are just like the doors from where the data passes from the network, and through which the data passes from the process to the network. It enters into your system and it leaves your system, right? So if you see over here, we have a socket over here. So the transport layer in the receiving host does not actually deliver data in the receiving host. So when it is received, for example here, it is not delivered directly to a process, but it is delivered to the socket, because at any given time there can be one or more socket in the receiving host, and each socket has a unique identifier. So the format of the identifier depends whether the socket is a UDP or a TCP. So let's consider how the receiving host will direct the incoming transport layer segment to the appropriate segment. Now each transport layer has a set of fields in the segment which have identifiers for this purpose. So at the receiver side, what happens? The transport layer will examine those fields. So transport layer will examine those fields, will examine that segment to identify the receiving socket number, and then it will direct that segment to that particular socket number. So this job of delivering the data in a transport layer segment to the correct socket is called as the demultiplexing. So the job of gathering data chunks at the source host will be later used for demultiplexing to create segments, and it passes these segments to the network layer is called multiplexing. Now transport layer is a middle host. So demultiplexing segments arrive from the network layer, and this is done by directing the arriving segments to the corresponding process socket. So if you see in this figure, host 1 using some process 3 is trying to send a packet to host 2 to the process 1, and over here the host 3 is using process 4 is trying to send a packet to process 2 on the host layer. So transport layer is a middle layer over here, or the middle host in the host number 2. So when the packet arrives at host 2, transport layer should demultiplex the segment which it gets from the network layer. Now after demultiplexing, it
I
is
losing it,
directing the
losing it.
arriving segments to the corresponding process socket. So if you see in this figure, host 1 using some process 3 is trying to send a packet to host 2 to the process 1, and over here the host 3 is using process 4 is trying to send a packet to process 2 on the host layer. So transport layer is a middle layer over here, or the middle host in the host number 2. So when the packet arrives at host 2, transport layer should demultiplex the segment which it gets from the network layer. Now after demultiplexing, it will direct the segment either to the process 1 or to the process 2 by checking the socket number provided in the arriving segment. So when the segment arrives at the transport layer, it checks the socket number. So based on the socket number, it directs the message to that particular application, because the processes have different socket numbers. Okay, so multiplexing occurs at the sending side, whereas demultiplexing occurs at the receiving side. All right, moving ahead. How the demultiplexing works. Now host receives IP datagrams. We have learned in chapter 1, network layer receives datagrams, transport layer receives segment. Demultiplexing always occurs at the receiver side. So host will receive the message in the form of the datagram. Each datagram has the source IP address and the destination IP address, and each datagram carries one transport layer segment, and each segment has a source destination port number, which we call as the socket number. So socket number is the combination of the IP address and the port number. So host uses IP address and port number combined together to direct the segment to the appropriate socket. Socket number of every application is the combination of the IP address and the corresponding port number. So let's understand how these are created. So connectionless demultiplexing. So how we can create with the programming. So datagram socket package, by using this package, we call it as the socket programming in Java. These are just for your information, the lines of code. We create an object of the datagram socket and we provide over here the port number. So this is another socket created and we provide some port number over here. So when a UDP packet is created in this manner, we are creating a UDP packet over here. When it is created in this manner, the transport layer automatically assigns a port number to the socket. So a transport layer assigns a port number in the range of 1024 to 65533. The port numbers range from 1024 to 65535. That is, and it checks a port number or assigns a port number that is not used by any other UDP port in the host. Java program can also create it can make it as empty, or it can provide over here the port number. So specific port number is provided. If you don't provide any port number over here, you keep it empty, then the Java program will, the transport layer will automatically assign the port numbers. Application developer writing the code were implementing the server side of a well-known protocol. Then the developer has to assign the corresponding port number. Now when the host receives the UDP with the segment. So with the let's understand more. With the port numbers assigned to the UDP sockets, we can now describe the multiplexing and demultiplexing. Let's assume that we have host A and host B. Host A has a port number something, let's assume 19157, and it wants to send an application some message to a UDP process to the host B, and let's assume the port number is 46428. So the transport layer in host A will create a segment that will include the message and the source port number, which is 19157, and the destination port number, and the two other values, which will be the IP addresses. And this segment will be passed to the network layer. Network layer will encapsulate the segment in the IP datagram and deliver the segment to the receiving host. Now, when the segment arrive at the receiver side, so the transport layer at the receiver side examines the destination port number. So when it checks the destination port number, kindly when it checks the destination port number, now at that particular point, the host B can be running multiple processes and each having UDP sockets. So UDP segments arrive, host B demultiplexes each segment based on the port number to their correct application. So UDP socket is fully identified by two tuple constraints, which is IP address and the port number, which is always called as the socket address. So when the host receives UDP segment, it always checks for the destination port, and the UDP it directs the UDP segment to the socket with that port. And IP datagrams with different source addresses, so IP addresses or source port numbers are directed to the same socket. Alright, so moving ahead. So if you see over here, this is the example that we discussed. Okay, so SP here is source port, DP means destination port. So for example, this process P2 wants to send a data message to some host, some other host. Let's assume that the IP address is A, the IP address is C, and the IP address is B. So when it sends, creates a data, creates a segment, it mentions the source port and the receiving port. So this is the source port and this is the destination port. So when the segment arrives over here, transport layer checks what is the destination port and it directs the segment to that particular application. Now after receiving the message, let's assume that the process 3 wants to reply.
Bro, I feel like it's so boring. I feel like I know this, but I gotta continue. I feel like this stuff is obvious.
And the it sends here 4 tuple: source IP address, source port number, destination IP address, and destination port number.
Actually, let me get up and stretch. Oh my god. Got this exam tomorrow. Uh,
So socket is identified by 4 things: IP address of the sender, port number of the sender, IP address of the destination, port number of the destination. Receiver host uses all 4 values to direct the segment to the appropriate socket, and the server host may support many simultaneous TCP sockets, because server may have many TCP segments or TCP sockets which are carried on at the same time, and each socket will always be identified by the 4 pair of things, which are sender IP address, sender port address, destination IP address, and the destination port address. Alright, web servers, they have different sockets for connecting to the client. Non-persistent HTTP have different sockets for each request. Okay, now let's talk about UDP. Moving ahead. Alright. So, UDP, User Datagram Protocol, no frills, bare bones Internet Transport Protocol. It's an Internet Transport Protocol, and It's the faster protocol, it's a connectionless protocol. Best effort service, UDP segment, it provides best effort service, but UDP segments may be lost, may be delivered out of order. Out of order means, suppose there are 10 segments to be delivered, so it may be delivered as four. First of all, fourth segment is delivered first, then eighth, then two, then one, like this. It is a connectionless protocol. That means there is no connection establishment, no proper connection establishment between the sender and the receiver, which means that there is no handshaking between the sender and the receiver. Each UDP segment is handled independently of others. So let's assume that there are 5 UDP segments need to be sent. Each UDP segment will arrive out of order and it will be handled independently at the receiver side. Now, there is no connection establishment which can add
Uh,
to the delay. There is no connection state at the sender, or the connection state is not stored. Small segment header, and it does not provide congestion control. But then why there is a UDP? Because UDP is a faster protocol and many applications may not require reliable, but sending the data at a faster speed is much more important, like the streaming applications. So that's why there is a need of the UDP protocol.
Alright,
There is no connection state at the sender, or the connection state is not stored. Small segment header, and it does not provide congestion control. But then why there is a UDP?
no
Because
congestion.
UDP is a faster protocol and many applications may not require reliable, but sending the data at a faster speed is much more important, like the streaming applications. So that's why there is a need of the UDP protocol. Alright, so moving ahead, our next topic will be the principles of the reliable data transfer. There are many applications which use UDP.
I feel like she just like UDP really just gets mentioned once and that's it. Why do we use it? Because it's faster. It says streaming multi. Why is there a UDP? Last way as fast as desired. Yeah, but this. Yeah, delivered out of order, lost. UDP segments may be lost. Delivered out of order. Connectionless, no handshaking. Usually UDP segment handled independently of others. Alright.
Especially the streaming and multimedia and internet telephony and network management. Many applications use UDP protocol. We are not going into much detail for the UDP, like its datagram structure or whatever. Now we will start with our the next topic, which is the principles of the reliable data transfer. So what is principle of reliable data transfer? Now in this part, we will actually focus on the problem of the reliable data transfer. That means there should be a reliability in the transferring the data in general context. So this is actually.
Oh, yeah, yeah, yeah. Oh, so yeah, there is gonna be. Alright, hold on. He. He. Another thing that's confirmed on my exam. He did say there's gonna be the internet checksum because I did ask him, and so confirmed it. Said, are there gonna be binary numbers? He said yes. So confirmed that this is going to be on the exam. So hold on. Let me stretch. I'm Luffy with the gummy neck. Alright, hold on. Alright, so that's gonna be that. Let me make sure I got this down before. So this is gonna be 26, 156 plus 62, 310, 88, 466. That's gonna equal, I believe it's, yeah, because if I do 26, 156 divided by 2, it's gonna be 1, no, it's gonna be 0, divided by 2, 0, divided by 2, 1. So, first thing I'm going to do is I need to remember that 0.5 Oh no, I could easily, okay, I will easily be able to. They're gonna be 44, 233, divide by 2, 116 equals 1. Oh wait, alright, now we got 2764, 1. Hold on. Why am I still getting notifications from this? Alright, 1382 equals 0. 691, 345 equals 1. 172 equals 1. 86 equals 1. 0. 43 equals 0. 21 equals 1. 10 equals 1. 5 equals 0. 2 equals 1. And then 2 divided by 2 is 1, so it's going to be 1 equals 0. So 1 0 1 0 1 0 0 1 1 0 0 1 0 0 1 0. What? 0 0 1 0. Well, yeah, 5. 10 divided by 2 is what? It's 5, but that would then be a 0, right? Oh, wait, no, wait. 21 divided by 2 is 10.5, so that's a 1. 5, 10 divided by 5 is 10 divided by 2 is 5, so that's a 0. 5 divided by 2 is 2.5, so that's a 1. 2 divided by 2 is 1, so that's a 0. How is this 0, 1, 0? Did I add these numbers wrong? Hold on. 26, 156 plus 62, 310. 88, 466 divided by 2. Divided by 2. Okay, so that would be a 0 here. Divided by 2. Well, 5529 is, wait, 11058 divided by 2. 5529 divided by 2. 2764, that's a 1. 4 divided by 2. 1382, that's a 0 divided by 2. 345 divided by 2. 172 divided by 2. Divided by 2. Divided by 2. Bro, what? Is there a space in this somewhere? That can't be incorrect. Let me see. 26156 divided by 2. 0, 0, 1. 3269 divided by 2. 1. 1634. 0, 1. 0, 0, 0, 1, 1, 0, 0, 1. Is there, wait, how does that even 26156 divided by 2? 0, 0. Hold on. This doesn't even make sense here. What did they give me? Oh, they gave me the complement? Wait, what? Signed two's complement. They gave me this right here. Yeah, this is what I did here. A466. Alright, let me see how this is. 0, 1, 0. 1, 0, 0, 1. 1, 0, 0, 1. 1, 0, 1, 0. Oh, 1 divided by 2, which is 1. But that's not... That's 16. Did I... 4, 8, 12... That's 17 bits, though. Hmm... That doesn't make sense. 8466. Oh wait, 88466. If I put this in, will it mark it as right? So if this ends with a 1, it's an overflow. I guess if it ends in a 0, then it doesn't matter. So if this is our... Then it's gonna be do. Wait a second. It's gonna be this. And if that was a 1, that's gonna be a 0 then. Oh, okay, okay. See, this is what sucks about for the exam. I can't check if it's right, so 77, 70. Alright, we're starting with a 1. My god. There we go. Oh wait, what? Nice. What? 4 equals 0, 2 equals 0, 2 divided by 2 equals 0, and then we're gonna have the 1 over 2, which equals 1, so it's gonna make this to be 0, 0, 0, 1, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1. But then we have the overflow, so I think it's gonna be this. Let's fucking go! 1, 1, 1, 0, 1, 0, 1, 1. 1, 0, 1, 1, 1, 1, 0, 1. Let's go! Baller! Shot caller! Alright, is this the first video? I think so.
About the principles of
No, it's not.
you can say this is relevant since the problem of implementing reliable data transfer not only is at the transport layer but also at the data link layer and the application layer. So it's a general problem of central importance to the networking. So let's first of all understand this. It's an important in all application, and but it's a problem in transport and the link layer. It's one of the top 10 list of important networking topics. So
Top 10.
reliability in providing the data transfer is when you are doing some research. It's one of the important topic, a networking topic. So before we understand this diagram, we must know that it is the responsibility of the reliable data transfer protocol to implement this service, and this task is actually made difficult by the layer below. The reliable data transfer protocol may be unreliable. For example, below the application layer, we have two protocols, TCP and UDP. TCP is a reliable data transfer, and but it is implemented on the top of IP, which is unreliable. So if you see, if we use TCP over here, below the net transport layer, we have a network layer, and the important protocol of the network layer is the IP protocol. IP is highly unreliable protocol. So a TCP, which is a reliable data transfer protocol, is implemented on the top of the unreliable, which is the IP protocol, end-to-end network layer. So we can say
Hold on.
of IP, which is unreliable, made difficult by the layer below. The reliable data transfer protocol may be unreliable. For example, below the application layer, we have two protocols, TCP and UDP. TCP is a reliable data transfer, and but it is implemented on the top of IP, which is unreliable. So if you see, if we use TCP over here, below the net transport layer, we have a network layer, and the important protocol of the network layer is the IP protocol. IP is highly unreliable protocol. So a TCP, which is a reliable data transfer protocol, is implemented on the top of the unreliable, which is the IP protocol, end-to-end network layer. So we can say that the layer beneath the two reliably communicating endpoints might consist of a physical link, which is the in case of the data link layer, or a global internetwork. So we can view that the lower layer is simply unreliable point to point channel, because when the data is sent, the link, the physical link, the path is also not reliable. So we can say that the data, reliable data is actually transferred on the unreliable channel. So we will actually understand this diagram, and we will incrementally develop the sender and receiver sides for the reliable data transfer. So let's understand over here. Uh, if you see over here, the sending process has the data to send, and it assumes that the channel through which it is sending is reliable. But actually, how the service is implemented over here, the sending side of the data transfer protocol. So here, the sending side of the data transfer protocol will be invoked from above by a call, by calling this method RDT send. RDT means reliable data transfer protocol. Now it will pass the data to be delivered to the upper layer at the receiver side. So when it is sent over here on the unreliable channel, it will be passed to the upper layer at the receiving side. It will be passed at the receiving side. Now on the receiving side, we have RDT receive, so reliable data transfer receive. It will be called when the packet arrives from the receiving side of the channel. So when RDT protocol wants to deliver data to the upper layer, it will do so by calling the deliver data. If you see over here, deliver data. So we use the terminology packet.
I hope for his multiple choice, like, they're easy to the point where, like, I wouldn't have to attempt to explain my answer in another free response, because if I choose an answer but I have an explanation for it, then I would like to have, I don't know.
Rather than the transport layer segment over here, because the theory which
Oh,
we are
whoops.
going to develop in this is not just based on the internet transport layer protocol. So the generic term most of the time packet is sent. So characteristics of the unreliable channel will determine the complexity of the reliable data transfer protocol. So the meaning
What? Hold on. Says the complexity of it's just backwards. Characteristics of unreliable determines the complexity, not complexity. complexity of the
Over here, the
reliable.
overall big picture is we have some reliable data transfer to reliable data to send, but the protocols which are operating below the layer or underlying or the physical links may be unreliable. Alright, so this is what I explained you right now. So RDT, reliable data to send, which will be called.
That's probably gonna be a question here. Like this, like he'll flip these two things, and I'm gonna have to figure out which one is it, reliable or unreliable. Complexity of reliable data, characteristics of unreliable.
Called from above, for example, by
Characteristics of
application,
unreliable.
and pass data to deliver the receiver upper layer, right? UDT send is called by the RDT to transfer the packet over the unreliable. So it will be called by the it will be called to send the packet on the unreliable channel. At the receiver side, RDT receive will be called when the packet arrives on the channel, and then deliver data will be called to deliver the data to the upper layer. Alright, so let's understand these RDT 3.0, which is a protocol in action. So we are going to understand both operations with no loss, although there are RDT 1.0, RDT 2.0, but we are going to understand RDT 3.0. What happens with the operation when there is no loss or when there is a lost packet.
Hold on. Let me try and remember this real quick. Complexity of reliable data transfer determines is characteristics of unreliable determine the complexity of reliable data transfer. Complexity of unreliable complexity of unreliable complexity of unreliable channel. No, what? Characteristics of unreliable. Why they gotta both start with C? Uh, characteristics of. That's gonna be one thing he's gonna do. He's probably gonna say characteristics of reliable, characteristics of unreliable. So it's gonna be characteristics of unreliable channel. So characteristics of unreliable determine the complexity of reliable. If I remember like CUR, I don't know, just make stuff up. Characteristics of unreliable channel. Complexity of reliable. Alright. Will depend strongly.
Now, in this protocol, we are going to consider,
Where
we are going to
the hell
take
image
four
is
scenarios
this?
when the sender is sending packets to the receiver, and there is no loss, there is a lost packet, there is a lost acknowledgement, or there.
Alright, what is this? Retransmit. Handles duplicates. Stop and wait. What is checksum? It's the goal of checksum is to detect flipped bits, right? Detect errors. I just say flipped bits. Detect errors in transmitted segment. Alright.
There is a delay in acknowledgement. So let's assume that sender sends packet 0 to the receiver. It receives the packet 0.
I understand all of
So
this
will
already.
send how long it at the receiver has passed again time, and now uh, it will send duplicate not know over here the timer. So now time is some pipe data packet is lost, acknowledgement is lost, data packet is delayed or acknowledgement is delayed, right? So we have some pipelined protocols. So protocol which we discussed now, it was RDT 3.0. It's a functionally correct protocol, but it is unlikely that anyone would be happy with its performance. So it is not, the performance is not well, especially in today's high speed networks. So the problem actually with this protocol is stop and wait. If you see, if you have carefully seen over here, the sender sends the packet, stops. When it receives the acknowledgement, only then it sends the another packet. So it is working like a stop and wait protocol. It sends the packet, stops and waits for the acknowledgement, then it sends the another packet again. So there is a performance problem with this type of stop and wait protocol, especially in today's high speed networks. So the solution to this problem is simple. Rather than to have stop and wait in this manner, sender can send multiple packets without waiting for the acknowledgement. And if sender is allowed to transmit.
See, if he asks, like, the opposite, where he says the definition and then asks, what is this? I'm gonna probably be lost. Maybe. Like, if he said, what allows you to send? Sender allows multiple. I don't know.
3 or 4 packets before having to wait for the acknowledgement, so the performance will be increased. Since many in transit sender to receiver packets can be visualized, this technique is known as pipelining. So pipelining means we have like designed a window has a size, for example 4 or 5. Sender can send 4 or 5 packets at a time. After all these 4 and 5 packets have been received by the receiver, and for all these 4 and 5 packets the acknowledgement has received, then the next packets will be sent. So this is called as pipelining. So sender allows multiple in flight yet to be acknowledged packets, right? So 5 packets are sent, first packet is not yet acknowledged, so it has sent multiple packets. Range of sequence numbers must be increased when this type of pipelining approach is used. Sequence numbers should be increased. There should be a buffering at sender and receiver size, and range of the sequence number and buffering requirement depend on the manner in which the data transfer.
If there's buffering, that means this is only a TCP action, right? Mm. I think this is just for TCP then, right? It doesn't seem like it, I don't know.
Protocol responds to the loss. So if you see over here, stop and wait protocol, one packet is sent, the sender stops and waits for the acknowledgement. Then another packet will be sent, sender will be stopped and wait for the acknowledgement. Now for the pipeline protocol, if you see over here, there a certain size of window is defined. For example, sender can send 5 or 10 packets, right? It has sent maybe 10 packets. Now it will wait to get the acknowledgement for this 10 packets, then it may send 10 or 15 packets again. Now range of sequence number can be increased. For example, it has sent first of all 5 packets, then it can send 7 packets or 8 packets. There are two generic forms of the pipeline protocols, which are go back N and selective repeat. Now these are an example of the pipeline protocols. We are going to discuss these two protocols, which are go back N and selective repeat. Now what is it? Go back N and selective repeat. Go back N. Sender can send N unacknowledgement packets. So N can be any number, 5, 10, 15, 20, 100. So sender can have up to N unacknowledgement packets in the pipeline. Receiver only sends cumulative acknowledgement. So receiver will not send acknowledgement for one by one. For example, if it has sent 10 packets, it will not send 10 acknowledgement. Rather, it will send acknowledgement and it will number it as 1 to 10. So cumulative acknowledgement are sent. But it will not acknowledge the packet if there is a gap. Sender has a timer for the oldest unacknowledged packet, and if the timer expires, it will retransmit all the unacknowledged packets. Alright, so let's understand this. First of all, we will understand go back N, then I will explain the selective repeat. So for example, there are k bits sequence number in the packet.
I already know this stuff.
Send
I talked to the professor today.
transmit 0. Uh, uh, Sender, so it sends acknowledgement 1 again. 2 out, the time out for the packet 2 is received, and 4, and it will send received sender side acknowledgement are sent. So it actually, again the set timer expires, acknowledges all commitments. White stand and blue means it is acceptable. Alright, so selective repeat. If the next available sequence number is in for packet received, so packet it will be buffered and it will send acknowledgement 3 and acknowledgement has expired side in advance. But
Alright, well, I already knew that.
in this lecture, we are going to continue with the remaining concepts of the transport layer, which is connection oriented transport, which is TCP. Then we are going to talk about principles of. Let's start with this. We have already talked about in detail regarding the TCP, transmission control protocol.
This is gonna be the last one that I do today, and then tomorrow I need to go back to chapter 4, do a refresher on that, and I should be good. My exam tomorrow is at 3 p.m.
which is an important protocol of the transport layer. It's a connection oriented protocol. Connection oriented means before sending data to the receiver, TCP makes a handshake or makes a connection with the receiver, a logical connection. So the connection is followed in the 3 steps. First of all, connection is established, then data is transferred, and then connection is terminated. So just quickly let's have an overview of the TCP, the characteristics of the TCP. First thing is it's point to point. There is a point to point connection establishment. So one sender, one receiver, just like the circuit switching. We talked about circuit switching also in chapter 1. It is also point to point, one sender and one receiver. Similarly, TCP is also point to point, one sender and one receiver. It is reliable in order byte stream. So it's a reliable protocol and it transmits the bytes or the data in order. So the data, how it is sent, it will be received in the same order at the receiver. There are no message boundaries. It's a pipeline. TCP congestion and flow control, it sets the window size. We learned about the two protocols, the pipeline protocol, how does the TCP sends the segments, like it defines a window, and in the window it puts like 3 or 4 frames. So as and when the frames are delivered, it keeps on adding the segments in the pipeline. So there are send and receive buffers at both the sides. So we have at the sender side there is a TCP send buffer. Buffer is nothing but a temporary memory location, and at the receiver side we have a TCP receiver buffer. So the TCP segment buffer, before sending, the segment is first of all saved in the TCP send buffer area. Then from the buffer area it is transmitted on the transmission medium. At the receiver side, the segment is first of all received in the buffer area, and after that it is sent to the application layer. Next is TCP is full duplex data. That means there is a bidirectional flow in the same direction. Full duplex means at the same time both sender and receiver can send. So actually we have the communication can be either simplex, half duplex, or full duplex. Simplex means only one side can always send, just like in the client and server. Server can always send, right? So, or we can say the master computer can always send. So simplex means the data always flows from one end only. Just like in your computers, data always flows from keyboard to the monitor. Never ever the data flows from monitor to the computer. So that's an example of the simplex communication. Half duplex means both parties, both sender and receiver can send the data, but at a particular time only one person. So for example, in half duplex, if the sender is sending the data, receiver cannot send. If the receiver is sending the data, sender cannot send. Example of half duplex is the walkie-talkies. You might have seen the walkie-talkie in the hand of the policemen or the security personnel which are standing on the airports, or the security guards. Last one is the full duplex. Full duplex is you can say quite more advanced form of communication. Full duplex means both sender and receiver can send data to each other and at the same time. So it's a bidirectional data flow. In half duplex also it's a bidirectional data flow, but only one can send at a particular time. So it's a bidirectional data flow in the same connection. So in the same connection, both sender and receiver can transmit at the same time. And it defines the maximum segment size. Maximum segment size means what is the maximum number of bytes that a segment can carry. Next is it's a connection oriented. That means there is a flow overwhelming.
Let's get to the next slide.
See this type of segment structure when we start with the Wireshark, maybe in week 5 in our lab. So we are going to talk about all these segment structures in the lab also. Okay, so the TCP segment structure, this is a TCP segment structure. These are the fields in the segment structure. The size of the TCP segment structure is 32 bits. Sorry, it's not 32 bits. Yeah, it's 32 bits. No, the size of the TCP header is actually 20 bytes. Source port and destination port, they are 32 bits. So the size is different. Let's talk about TCP header is 20 bytes. But whereas UDP header is, I think it's 8 bytes. UDP header is 8 bytes and TCP header is 20 bytes. This is TCP header or the segment structure. This is 20 bytes. So let's talk about the TCP segment. It is almost some fields are similar to the UDP segment or UDP datagram. Okay, so let's talk about this one, source port and destination port. Source port and destination port number are used to specify the port number of the source application and the destination port number of the source application. Next we talk about sequence number. Sequence number is 32.
Who's lurking? It says I have 2 viewers. Who's lurking out there watching, chilling? I'm on to you. What's
Bits,
up?
that means 4
Hello.
bytes, and acknowledgement number is also 32 bits. These are used by TCP sender and receiver.
Are you just chilling, doing homework while I'm also studying? And then I'm just like, who are you? I see you. Oh my god. Sorry. You're probably just like, I'm just doing the same thing you are.
For sending the reliable data transfer service. After this, we have a receive window. Receive window is 16 bits, that means 2 bytes. This is used for flow control, and this is used to indicate the number of bytes that receiver can accept from the sender. Then we have the header field over here, header length field. This is a 4 bit, sorry, not even a byte, it's 4 bit. It specifies the length of the TCP header in 32-bit words. TCP header, it can be of variable length. It can be of variable length because of the TCP options field, because options, this is of variable length. It can have any size. Then we have over here options field also. This one options field. Options field is of variable length, and it is used when a sender and receiver negotiate for the maximum segment size or for a size of the window or the window scaling factor. Now, if you see this part is not used. Then we have, if you see UAP.
I like how it's just called not used. What?
RSF. These are the flags, 1 bit each. So there are 6 flags. So this is 1 bit each, and total they carry 6 bits. So the flag field contains 6 bits. Now we have A stands for acknowledgement flag. It is used to indicate that the value is carried in the acknowledgement field is valid. Then we have reset, SYN and FIN. So this one, R, S and F. Reset, SYN and FIN. These flags are used for the connection establishment in the beginning and for the connection termination at the end. Then we have this P flag. It stands for push. It indicates that receiver should pass the data to the upper layer immediately. And finally we have this U. U stands for urgent. Urgent bit is used to indicate that there is data in this segment that the sending side upper layer entry has marked it as urgent. And next we have the urgent data pointer. If you see over here, urgent data pointer. The location of the last byte of this urgent is indicated in the 16-bit urgent data pointer, and TCP informs the receiving side of the upper layer when there is some urgent data, and it needs to pass it a pointer to the end of the urgent data. Checksum is used to calculate the errors. If there are errors in the data when it is received, so this field is used to check the errors. It performs some calculations on the received data. Push data, P is not mostly it is not used. Urgent is also.
It's not. Oh man, we don't push P. Push data now, we don't push P. No.
Also, urgent data is also generally it is
We good. Come on.
by user acknowledgement on the segments, so as the segments can be differentiated from each other. So these are two important fields, sequence number and the acknowledgement number, and these are the critical part of the TCP's reliable data transfer service. So sequence number, what is a sequence number? It's a byte stream number of the first byte in the segment's data. So every segment is always numbered by the TCP. So sequence number is just a number on the of the first byte in the segment data, and it is chosen as a random number. Okay, so now what is acknowledgement number? It is the sequence number of the next byte expected from the other side. It can be the cumulative acknowledgement also. Alright, now let's check over here. We have host A and host B. The first host A, let's say it types letter C in the segment and sends it to the host B. Puts the sequence number 42 as a random number chosen for the first byte in the segment data. Acknowledgement number is 79 and data is C. Now after host B receives this data, it has to send the acknowledgement. Now in the acknowledgement number, the sequence number will be whatever the first segment that sender has sent to the receiver. So this acknowledgement number will become the sequence number in this acknowledgement segment. Now this is the acknowledgement segment. Now here, if you see over here, acknowledgement number is 43, but here the sequence number for 42. Now what does acknowledgement number specifies here? The acknowledgement number specifies here the next expected sequence of the segment which the source must send to the receiver. So this means that the next segment that host A will send to host B, it should carry the sequence number 43. This is what is the purpose of the acknowledgement number. So acknowledgement number specifies the sequence number, the expected sequence number of the next byte which the sender will send to the receiver. Now host A receives the acknowledgement and then it sends the final segment for connection establishment or whatever. So if you see over here, the sequence number is 43. Whatever the acknowledgement number was here, sequence number is 43, and here the acknowledgement number is
What's up,
incremented by
Coast?
1. So this.
What is that emote? Has O? What is that emote? Ugly ass emote. Yeah, I know, this is boring. I know. Been filling this shit up in my head for the past 3, 4 days, 5 days, past week actually. Oh my god, if I don't get an A on this exam, I don't know what I studied. But I don't know, I feel like he's gonna throw some oddballs. Like he can ask one question studying, I know. But doing all this studying and made me realize once summer starts, I got so much shit I'm gonna do. Like once I'm done with work during the summer, I'm probably gonna be streaming, programming either my music site or playing games, cause I just I don't have to worry about anything else except work the next day. Oh my god, the school stuff is just not for me. It's just I'm not learning. Like literally, I'll tell you this, next semester I will not remember any of this, nor will I care about it. It's just there's it's just such a waste of time for me, but I got I got another semester left, so I might as well finish it. But oh my god. Thing is, I'm afraid about this exam because I showed earlier my grade and what I needed on this exam to pass the class basically. So this is my current grade. Yikes. Yeah. But if I get like a 50 on this exam, that's a 50%. I'd have a 65. I'm still passing. Even if I get like a 25, that's passing. So that's good. But I'm hoping if I get like, cause if I get an 80, I'll have a 71. What's the lowest I can get? Let's say if it's 75. Yeah, I could get. Oh no, I could go lower than that. Yeah, so I can get a 71 on this and have a 70 in the class, but everything else here needs to be graded. But if I click on it, I know potentially two questions. I don't know the exact questions, but I know what they consist of. So there's 24 questions, 100 points. One of them consists of, where the hell is it? This checksum. It can one question is this, so I know how to do this. Another question is has the something to do with this. So he said, like I know what these do, but he said that we don't need to memorize any formulas. But I need to email him a question about the others. There's something else in here I need to email him about. The conditional. Alright. But yeah, I'm just gonna finish up this video and be done for the night with studying. Because there's some other homework assignment that I want to try and get done tonight because I don't think I'll have some. I don't. It's due Thursday, but I don't think I'll have time that tomorrow afternoon. So I want to try and get it done tonight.
This is how the connection establishment takes place, and this is how the exchange of messages takes place. The first sequence number is just a random number chosen by the host, and even the acknowledgement number. After that, it should be in the increasing order. If you see the acknowledgement number,
Fuck
the
are
first
we?
acknowledgement sent by the receiver is the increment of the first sequence number, and the
Bro,
second acknowledgement number sent by the sender is the increment of the first acknowledgement sent by the sender.
bro, where the fuck? It's right here.
Now, if there are out of order segments received by the receiver. So for example, sender has sent 4 segments. So receiver first of all receives segment number 2, then it receives segment number 3, then it receives segment number 1, and then it receives segment number 4. So these segments have arrived out of order at the receiver. So how does the receiver handles these out of order segments? So TCP does not specifies anything for handling the out of order segments. This is up to the software developer or up to the implementer how to handle these out of order segments if TCP protocol is used. Alright, now TCP, RTT and timeout time. We discussed about RTT in the previous lecture and timeout time, because each packet has a certain time specified, maybe 150 milliseconds or 100 milliseconds something. So in that time period, segment is sent and acknowledgement must be received by the sender. So that is called as time during that time lapse. So if during that time lapse acknowledgement is not received, that means sender will assume either the packet is lost or the acknowledgement is lost. Now the question is how to set the TCP timeout value, how the timeout value is sent. It should be longer than the round trip time. Right, we understood the round trip time also. It should be timeout value should be a little larger than the round trip time, but round trip time varies for each segment. If the segment is large, round trip time may vary for it. So timeout time should be larger than RTT round trip time, but how much larger? Should it be too large or how much larger? Now, if it is too short than RTT, then there will be a premature time and there will be unnecessary transmission. So for example, if RTT round trip time is maybe 100 milliseconds, alright, so and if we give time out time as 80 milliseconds, in 80 milliseconds the segment may not be received or acknowledgements may not be received. So there will be unnecessary retransmissions, there will be unnecessary duplications occupying the buffer. But if it is too long, then there will be slow reaction to the segment loss. Either the receiver has to wait for a longer time or the sender has to wait for a longer time to react that a particular packet is not received or a particular acknowledgement is not received. So it should not be too longer than RTT, or it should not be too shorter than RTT. So how to estimate the RTT? Now the question is, we have a sample RTT. Sample RTT is measured, it's a time which is measured from the segment transmission until acknowledgement is received. So a sample RTT, when the first segment is sent, a sample RTT is measured. So when the segment is sent and after how much duration the acknowledgement is received. So this forms the sample RTT. It is this time is measured, segment transmission until the acknowledgement received. So retransmission, we are not going to count any retransmission time. For example, if this segment is lost, we need to send it again, or this acknowledgement is lost, we need to receive it again. We are not going to count any retransmission time. Sample RTT will vary, and we want another estimated RTT. So estimated RTT is the average round trip time of the several recent measures. It is not just current sample RTT. Sample RTT is actually the round trip time for maybe one or two segments, but average RTT or the estimated RTT is the round trip time which we average for several recent measurements. For example, it can be for the first 10 segments, or can be for the first 15 segments or something like that. Because the sample RTT time will fluctuate from segment to segment because of the congestion in routers and varying load on the end systems, and because of these fluctuations, any given sample round trip time may not be of any use, or it may be atypical. So in order to estimate a typical round trip time and in order to be more calculative, that's why takes sort of a average of sample RTT values. So TCP maintains an average called estimate RTT of the sample RTT values, and after obtaining a new sample RTT, TCP updates the estimated RTT by using the formula. We are not going to discuss the formulas and not going to discuss much in detail. Alright, so that was the segment structure. Now we talk about the reliable data transfer. How does the TCP handles the reliable data transfer? Although these are given much in detail, this one segment structure, but we are not going to talk much about it. We discussed that TCP creates RDT, reliable data transfer service, on the top of the IP. Transport layer is
I don't know why.
uses creates network layer. So TCP's reliable data transfer service ensures that the data stream and the process reads out of its TCP buffer is not corrupted. It is without gaps, without by the end system. So what is sent is exactly what is received.
If he made it all multiple choice, I'd probably get an A.
So that is about the
That's the reason why I'm studying so hard, because it's not all multiple choice. It's like, I'd say good 20% of the grade is multiple choice and the rest 80% is free response, and I'm just like, bruh.
Reliable data transfer. Now it uses the pipeline segments, cumulative acknowledgements, and it uses single retransmission timer. We discussed the pipeline segments in the previous lecture, cumulative acknowledgements in the previous lecture. Now the single retransmission timer. So TCP timer management use only single retransmission timer even if there are multiple segments have been transmitted but not yet acknowledged segments. So this actually provides a reliable data transfer. Retransmissions, if there are needs to be retransmissions, how they can be judged or how they can occur by using the timeout events or by using the duplicate acknowledgement. So with if the within the timeout period, the within the timeout period, the acknowledgement is not received, so then the retransmission of the segment will occur. Or if a sender receives a duplicate acknowledgement, so that means the receiver has not received a particular segment, it will send that segment again. So this is how the decision of retransmitting a segment by the sender is done. Initially, it considers a simplified TCP sender, and it ignores the duplicate acknowledgements, ignore the flow control and the congestion control. So what are the sender events, TCP sender events that are done? Data is received from the application, because at the top of TCP, at the top of transport layer, we have the application layer. Data is received from the application layer. After receiving the message or the data, TCP creates a segment. When TCP is used, we call it as a segment. When UDP is used, we call it as a user datagram. So a segment is created with the sequence number. Sequence number is nothing, it's a byte stream number of the first byte in the segment. It starts the timer if it is not already running, and it waits. There is also a timeout interval, which is called as the expiration interval. So if during that timeout period, within that time frame, the acknowledgement is not received from the receiver, it will retransmit the segment because it caused the timeout, and it will restart the timer again. Sender will restart the timer again. Now acknowledgement, if after the acknowledgement is received, if acknowledges previously unacknowledged segment, so if the receiver has acknowledged the previously sent but unacknowledged segments, sender will update what is known to be acknowledged. So sender will update that, for example, sender has sent 4 segments, right? So receiver has acknowledged first 3 segments. So it will update that first 3 have been acknowledged and the last one is yet to be acknowledged, the 4th segment. It will start the timer if there are outstanding segments. Now let's talk about the flow control. So flow control, to handle the flow control so that the TCP does not overwhelms the receiver, there are sender and receiver buffers. So we have a TCP data in buffer and a spare room. So receiving side of a TCP connection has a receive buffer. This is, for example, a receive window. This hole is for the receiver buffer. Half of it is occupying data and half of it has a spare room to put the more incoming data. Application processes, why we have a buffer? Because application processes may be slow at reading from the buffer. That's why everything is first of all stored in the buffer of the receiver, and then one by one it is delivered to the application layer. So flow control is basically sender will not overflow the receiver's buffer by transmitting too much or too fast. So for example, receiver buffer may handle only 30 segments in a while. So flow control means sender should not send too many or at such a speed that receiver cannot handle the segments. There should be a speed matching between sender and the receiver. So matching the sending rate to the receiving application's drain rate, that is called as the flow control. Alright, so we have over here the explanation. Now for example, suppose TCP receiver discards out of order segments, right? So just like we did in the go back N protocol, so let's assume that if some out of order segment has arrived, it discards it. So now there is a spare room in the buffer, and how the received room size is calculated. Received buffer, whatever is the size, minus last byte received minus last byte read. This is how the formula is done. And receiver in the beginning, it advertises the size of its buffer, or we call it as the spare room, by including the value of the receive window in the segments. Sender limits unacknowledged data to the receive window. That means it guarantees that it will not full the buffer of the receiver. Alright, so that was about the characteristics of the TCP. Now we move on to the next part, which is the principles of the congestion control. Congestion is there are too many things on the network, right? So there are too many sources sending too many data very fast, and it is not possible for the network to handle all those data. So in that case, what will happen? Some of the data will be dropped or it will be corrupted, just like you have experienced congestion on the road. So for example, if we have a road, the road is designed to handle, like for example, 5 cars at a particular time. Now consider a case when we have 500 cars on the road at a particular time. So cars will be moving very slowly because the road is quite narrow. So that is called as the congestion. So congestion means when too many sources, they are sending the data too fast for a network to handle, which becomes difficult for the network to handle. Congestion control is not related to the flow control. So what happens in this case? Some of the packets will be lost or some of the packets will be delayed. So what happens during the congestion on the network? Either you will take too much time to reach to your destination, or you will change your route. So that means the packet is lost or you will not go anywhere. So it's one of the top 10 important problem in the computer network research.
Top 10, top 10.
Alright, so we have two broad approaches to handle the congestion control: end-to-end congestion and network assisted congestion. Now what is end-to-end congestion and what is network assisted congestion? Let's talk about. So let's talk about end-to-end congestion control. In end-to-end congestion control, the network layer does not provide any explicit support to the transport layer for the congestion control services. So there is no explicit feedback from the network layer regarding the congestion control. Network layer does not provide that there is congestion on the network, you should send less number of segments or something like this. Even the presence of congestion in the network must be inferred by the end systems. So it is the responsibility of the host to sense about the congestion in the network based on the observed packet behavior. So if it is taking too long for the receiver to receive a packet, receiver can infer that there can be congestion on the network, or if the sender is receiving duplicate acknowledgement or no acknowledgement during the timeout period, sender can sense that there is a congestion in the network. So it is the responsibility of the end systems to infer the congestion on the network based on the observed based on the packet behavior. This approach is taken by TCP. So TCP must necessarily take this end-to-end approach towards the congestion control, because IP of the network layer does not provide any feedback to the end systems regarding the congestion control. So TCP segment loss or the acknowledgement loss or the duplicate acknowledgement is taken as the indication of the network congestion, and TCP decreases the size of the window accordingly. Next approach to handle is the network assisted congestion control. So as the name says, there is no feedback from the network, but there will be a feedback from the network. So with the network assisted congestion control, the network layer components, for example the routers, they provide the feedback to the sender regarding the state of the congestion on the network. Now this feedback can be in the form of the single bit indicating the congestion at a link, or it can be in the form of explicit read. A sender should send at, and this approach is used in the ATM available bitrate congestion control. So This approach was also taken in the early IBM systems, and it was proposed for the TCP/IP networks. Alright, so let's now move ahead. Let's talk more about the TCP congestion control here. So that was the two approaches that we can take for the handling the congestion control. Alright, so how does the TCP senders determine their sending rate, such as they don't uh, congest the network and at the same time make use of all the available bandwidth? So TCP answers both these questions, how it determines the sending rates. They don't congest the network, and at the same time it makes use of all the bandwidth or the bandwidth that is provided to the TCP for its transmission of the segments. TCP answers these questions by using the following guiding principles, which we are going to learn in this slide. Alright, so for the first point here, congestion of the network. So lost segment implies congestion, so TCP, the sending rate of the TCP, sender's rate should be decreased, so when the segment is lost. An acknowledged segment indicates that the network is delivering the sender segment to the receiver, so sender's rate can be increased. So this is how the TCP can adjust to the congestion rate of the network. Second is bandwidth. Now TCP's strategy for adjusting its transmission rate is to increase its rate in response to the arriving acknowledgement. So if the acknowledgement arrives quite earlier than the timeout period, that means within the half of the timeout period or before the half, so it adjusts its time of response. It increases its time transmission rate in response to the arriving acknowledgement until a loss event occurs. So after that it decreases its transmission rate. So for example, if the acknowledgement arrives within half of the timeout period, it will increase the number of segments. It may send 2 segments again then. So until that event, when the loss of the acknowledgement is encountered or loss of segment is encountered, after that it will decrease its transmission rate. So these are the two approaches used by the TCP. Alright, now for handling the congestion control at each side of a TCP, that means at the sender and the receiver, what are the things required? We have a receive buffer at the receiver side, which will store the segments before delivering it to the application layer. Sender side will have a sender buffer which will store the segment before sending them on the transmission medium. And we have several other variables like last byte read. It tells us what was the last byte read. RWND stands for received window. It is the size of the received window, that means the size of the buffer. TCP congestion control mechanism operating at the sender keeps track of another variable. We have the congestion window, which is denoted by the CWND. So at the sender side there is another variable which is called as the CWND, congestion window, and the purpose of this window is to impose the rate at which sender can send the traffic. So basically this CWND variable or the window keeps track how many segments at a particular time a sender should send, so as to keep track of the congestion control on the network. Alright, so how should a TCP sender determine the rate at which it should send? So sender limits its transmission like last byte sent minus last byte acknowledged. For example, sender has sent 4 bytes, 1, 2, 3, 4. So it should be less than equal to the congestion window. Let's assume that the variable in the congestion window is 6. So last byte sent is 4, and maybe the last byte acknowledged is 2. For the first 2 the sender has acknowledged, so 4 minus 2 is 2. It should be less than the size of the congestion window. This is the formula used. or roughly we can say that sending rate should be equal to the congestion window size divided by round trip time. It is measured in the bytes per second. Congestion window is a dynamic function. It can be increased or decreased based on the network congestion. How does a TCP sender perceives that there is a congestion on the path between itself and the destination? Of course, simply by the loss event. It can be simply by the loss event, or there are duplicate acknowledgements. So it is either by the timeout, or that means no acknowledgement is received, or 3 duplicate acknowledgements from the receiver. So in that case, TCP sender will reduce the size or the rate of the congestion window after the loss. So there are 3 mechanisms for this: AIMD, slow start, and conservative after timeout events. So what is AIMD? AIMD is additive increase, multiplicative decrease. So these are the 3 mechanisms: AIMD, slow start, and conservative after timeout events. So either additive increase, multiplicative decrease, or in the beginning should be slow, that means should be slow in sending the segments, or it should after the timeout event occurs, it should be conservative, that means it should decrease the rate of the size of the congestion window. All right, okay. So AIMD, we are going to talk about the first approach. Additive increase and multiplicative decrease, we are going to talk only about this approach. So this approach increases the transmission rate. Transmission rate is window size, probing for a usable bandwidth, because at the same time TCP has to utilize the bandwidth at the full rate until the loss occurs. So additive increase the congestion window by 1 maximum segment size every RTT. So for example, first send only 1 segment, then 2, then 3, then 4. This is additive increase, right? We are increasing the size of the congestion window. Multiplicative decrease, cut the congestion window in half after the loss. If loss occurs, cut the size of the congestion window in half. For example, first segment is sent, then second, then third, then fourth, then 5, then 6. So the size of the congestion window is like 6. Now for example, at this time, the size of the timeout event occurs, so it will cut the size of the congestion window to half at this point, that is 3. So for example, if it is starting sending additive increase in the increase, and if it occurs like for example congestion here, it's a multiplicative decrease. At this point, for example, the size was like congestion window 16 bytes. So at this point the timeout event occurs. So if you see over here, the congestion window is reduced to half, which is 8. So again, when it starts sending linearly, it is increased. At this point, if the timeout occurs, it is the congestion window size is reduced to half. So this is the approach of additive increase, multiplicative decrease. Okay. So slow start. What is slow start? Slow start means it starts the congestion window by 1 MSS, 1 maximum size segment. So for example, let's consider over here MSS is 500 and RTT is 200 milliseconds. So it will measure the initial rate, how to utilize the bandwidth. And how to utilize the bandwidth, we have over here the sending rate should be in the bytes per second, congestion window by RTT. So we can calculate over here the size of the congestion window divided by RTT. Congestion window will be calculated by MSS. We will convert this MSS into, because it is bytes, we will convert it into kilobytes. So 500 divided by 1000 will make it 0.5 kb, right? And RTT is 200 milliseconds. We will convert it into milliseconds, seconds. So 200 divided by 1000, because in a millisecond there are 10 to raised to the power minus 3 seconds. So it will be 0.2 seconds. So we can calculate the sending rate. Sending rate is 0.5 divided by 0.2.
I'm gonna be honest, I lost interest in this studying. I started doing my other homework assignment. I think I'm gonna end my stream unless people want to see me do my homework assignment. I don't. I could do that. I guess I could do that. Alright. So let me close that. Let me try this. I don't know. My homework assignment is this. Change the title. Alright, so this is my homework assignment. So let me just make sure O can be fused with O, A can be fused with O, or B can be fused with B or O, AB can go with AB, A, B, or O. So I gotta do something like that, but then I gotta make sure this is how I'm doing it, but I don't know if this will work here, but I will see. That works. That works. That works. Oh, that works. Alright, let's see if this one works. Moist Critical is live. Alright, what is this? Declaration of exists. Uh-huh. Alright, let me see. This is the most fucked up programming language that there is, and I don't like it. What is... So it's if exists here. Uh, guess I don't need this because... If... I don't know how to do this. If this... Let me try that. I still think if exists should be it, but let me... Let me see. If not... Let me try that. Missing decoration of blood endpoint. Uh, I think. Uh, bro, what? I don't know how this works, to be honest. Undefined variable, blood 1, blood 2. Alright. Expected function. Expected integer or float. No. Do, do, do. But then if it says not emergency, like what? Test. Oh wait, maybe, hold on. Let me try this. Uh, Missing decoration for test. Hmm. Maybe I don't need to do this. Patterns matching facts are only allowed in the condition of not in the actions of the rule. You can either use multiple rules to determine which person to change or apply. So it has to be separate. Or, wait, it says, or you can use the fact set query functions to locate and change a person based from the actions if any fact P. Let me see. Any fact P. What? Okay. What? Uh, okay, let me try this. Based on this, it's saying this. If blood input mode 1 of, it says person. So this can be blood type 1 equals dash blood 1 name. Uh, wait, person. Oh wait, def template. It's gonna be blood types def then. Question mark n then I try that. Uh, blood missing function decoration blood input. It says any fact. I guess. Hold on. Function missing decoration. Any fact P. I'm gonna just put this because I don't know. Undefined def template, blood type 1. Oh wait, because that's this. Undefined template, blood types def. Isn't that this? Yeah, undefined template. Oh wait, should be this. I think this has to be like that. Uh, check appropriate syntax for fact set. Uh-huh. So I think what I gotta do is this. Stops here. I think it's because I gotta do this here. Hmm. Alright, let me just do one. If I can get one of these down, then I could probably add the other after. Check appropriate syntax. Looks like EQ. This has to have this. That has to have that. Uh, undefined variable exclamation point n. Let me see. Was oh okay. Uh, exclamation point end is blood one. I don't know if that worked. Uh, let me see if it does not equal. Hold on. Let me just do this then. Run A B. Uh, it didn't do anything. Alright, hold on. Let me get this other thing up and running. Oh, there's an and. I think that has to go away. Wait a second. Huh. Alright, hold on. I don't think. Hold on. I think I just have to do this. And then do run A and B. Well, A and B don't. Hmm. A and B. O, M. It's not working. It's not working. Oh wait, it looks like do for fact. Looks like I gotta do something like with this. Then do for fact. Do something like that. Do for fact. Ay, ay, ay. Alright, let me, hold on. Let me try what I had prior. Person is the def template, so I think I'll do this, right? I wanna at least get this part set today, where it can work. And tomorrow afternoon I'll get the other half done. Check appropriate syntax, blood input. I think I gotta do then. What did it? Oh, it ran. Okay. A, B, reset, run. A, reset, run. B, B. Why is it inserting it? It's assert. I'm doing assert, but I don't think it's supposed to do that. The Eevee laugh is being used. Haha. It's. Hold on. It looks like I gotta do this thing here. Bind, and then do this. And then at the end of this, I do assert, and then it looks like I just do blood types entered. Blood types entered A and B. But then we do this, then we do if they are compatible, then we do what? We do this, we're gonna do something like, where's the other, not that. I think we're gonna have to do something like, If exists inside of this. Oh wait, we could do this. Hold on. So it binds it, and then it does. Hold on. So this is our def template. Where's their def facts? Doesn't look like there is one. Alright. Okay, so def rule 2. Birthday name. Then we do data. Or no, hold on. We could do this. If it says whose birthday is it today, then rule 2. Okay, I think I found what I need here. Sound. Hold on. Okay, I think I found what I need. Sound exclamation point X. If we do this, and then here we do not, but it's gonna be inside of the def template for. Mm, so I think this should be blood import. Yeah. And then this, if they're not, and then it's gonna be, then I'm questioning on why I even have this. What? How come? Bro, what is going on? Oh wait, I think... Okay, hold on. What we gotta do is this. What? How? That doesn't make sense at all. This doesn't make sense at all. Okay, blood type A. What's the blood type? It's A. And then B. F10 equals A and B. It doesn't fire the next one. Which I think it should. Let me try this instead. Uh-huh. So it got fucked up, huh? Run A, B. See, look, it asserts the whole thing in there again. Like, what? Huh. Okay. So then how come? Oh, you know why? Because it resets it, that's why. So if I do facts, there's only 9. But then when I hit run, A and A, O, run, A, B, hmm. If they're not, maybe it's because of the space? Run, A, and B. But if it's not compatible, oh wait, let me try taking that out. Wait, no, if it, hmm, No, no, no. We can retract and do a printout. If not, here, I'm gonna just take this out and then just put this here. A, B, 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 and then C. If they're not compatible, then how come? I think it's because of this. This is messing things up here, I think. Hold on. Fax. Run. A and C. Reset. Run. A. C. Reset. Run. A. B. And A. I did it. I did it! Alright, and then let me add this. So, do 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 do. Hold on. Alright. And then, hold on. So now we have to do something with this if it's not a blood type. Do 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 do. So if it's not a blood type, if the says assert value, retract n. So if value, that's how we're, if, what's up? I got another viewer. What's up? Is that Coast? Trying to figure this out. I got the main homework part done, but now I gotta do something similar to the example my professor gave. Ask the user to enter value if it's not a certain value. So, for this programming language, whatever, if you can call it a programming language, is fucked. This shit makes no sense. It just doesn't make sense, bro. Like, it utilizes certain aspects of programming, but then some of it just doesn't. And I'm just like, why? Why? Bro, this shit doesn't make sense. Alright, hold on. If... Could I do... Let me try this. Uh, run. What? Reset. A. Oh wait, reset. I wasn't supposed to put an A. B. J. K. Alright, so... And then A to end it. So I'm gonna say if input... What we really need to do is copy this. So let's say this, and then we do this. So if we read value, which is read, if we assert this to this, then I think what we can do, oh wait, I think then we could do this, and I think we could do that, and then assert need. Oh shit, hold on. I ended up fucking myself over here. Oh god. Oh wait, I don't need to... Alright. I can do this. If I take this, uh, no. Take this, and put it here. Alright, I think this will work. So I take this one, take this one, and then I take What is this need? I don't know what that is. Check appropriate syntax for def rule. B, C. If value is not B, it didn't rerun it. Uh, oh, because it needs to assert need, which I guess we need to do this then. Let me see. B and then H. I fucked it up. I fucked it up. It broke. It crashed. I, I crashed it. Oh my god. I crashed it. You know what that means? I'ma be done. I got a whole pizza there. Alright, what time is it? 9:50. Damn. How do I do this thing? Alright, hold on. We're gonna raid, it's Chris. I'm gonna end my stream. Who was here? Whoever was here, watching, chilling, you a real one. Uh, did I do that right? One viewer is ready. Nah, come on, there's two people here. Come on. What? It says there's two viewers. How come it says one viewer's ready? Damn. Someone leave. Alright, well, I'm gonna be streaming not tomorrow, because I got things to do tomorrow. I'll be streaming later this weekend. Peace.